And my story couldn't be complete without talking about the connection between MLE and KL-divergence. But I will assume nothing about you knowing either. Well, by now you should have watched MLE, what is the maximum likelihood estimation. But I will introduce some of the KL-divergence prior information in this subsection. So first, let's talk about how to measure information. In communication, we exchange signals to convey message. Notice information is a very vague word. It's just an intuitive notion. So intuitively, one message is not always equal to another message, right? So if we speak colloquially, like when we invoke theorems that we don't understand, or theories, so we just say, one message conveys information, and this information is how can we measure messages? And necessarily we have to make very thoughtful, smart faces when we speak about that, so no one asks us about what information is and how to measure it. But if you think about for some time, well, maybe quite some time, it took humans, researchers, quite a lot of time to figure out how to measure information content of messages. But I'm sure if you spend enough time on it, you'll arrive at the following requirements based on the following assumptions. Yes, and under the following assumptions. So, messages are strings of characters from a fixed alphabet. That's important. The amount of information contained in a message should be a function of the total number of possible messages. And if you have an alphabet with S symbols, then there are S power L messages of length L. That's clear. Think about it. The amount of information contained in two messages should be the sum of the information contained in the individual messages. The amount of information in L messages of length 1 should equal to the amount of information in one message of length L. That's clear, right? So those are requirements. What can we do? What can we use to measure this information content given the simplified settings using some simple computable function? In 1928, Hartley suggested the following measure. Basically, he claimed, and we now agree, that the only function which satisfied all of these requirements is L log S, or log L S power L. So S is the number of symbols in the alphabet, and L is the number of is the length of the message, right? Length of the messages. The only caveat with his suggested information measure is that it works for, or kind of implicitly assumes that all symbols are equally likely. It's like when all symbols are equally likely in a message, then this information works quite well. This measure works quite well. Shannon, 20 years later, after that, went a little farther with the information measure, and the settings is slightly different. What if the symbols have different probabilities? So let x be a discrete random variable with n outcomes. Those are our n symbols in our alphabet, x1 through xn. And the probability that the outcome will be x sub I is probability of x sub I here. The average information contained in a message about the outcome of x is this, or the same could be written in differential information form. And when we do that, if we do, I don't want to copy all of that, but you get the idea, bx by. This actually is expectation of bx by. Well, this is a slight stretch. Differential entropy, the continuous form of the entropy, has some nasty behavior at times, but it's a good measure nevertheless. For continuous, for discrete definition or for discrete signals, discrete alphabet X, this is how Shannon defined the information measure. So as with Hartley information measure, we're still using the log of the log function to flatten out some variations, and otherwise also in the case when probability density is uniform, so each symbol is equally likely, we arrive at Hartley information. Okay. Oh, wait a second. So one thing, we're talking about information. Why entropy? Why do we call it entropy? Well, think few people. Boltzmann first, the physicist of thermodynamics fame, and then Gibbs, another thermodynamics physicist, and then John von Neumann, who knew what Shannon is working on and suggested, in his word, the following suggestion. Basically, von Neumann told Shannon the following words: you should call it entropy for two reasons. In the first place, your uncertainty function has been used in statistical mechanics under that name, so it already has a name. In the second place, and more important, no one really knows what entropy really is. So in a debate, you will always have the advantage. Okay, entropy. But what if the signal that is incoming, or the signal that is being generated, is generated according to probability X, but we encode it with an optimal code constructed for probability Q, probability distribution Q. We measure the number of bits needed to send a message containing symbols drawn from probability P when we use a code that was designed to minimize the length of the messages drawn from probability Q with cross entropy. Again, number of bits needed to send a message containing symbols drawn with probability P, but using code designed for symbols generated with probability Q. Obviously, since the code was designed for Q is suboptimal, it is suboptimal for P, and cross entropy is higher than if we used the optimal code for P. Okay. Now we have everything we need to talk about Kullback-Leibler divergence, KL-divergence. KL-divergence is defined as an expectation with respect to probability P of the log of ratio of probability P and Q, or this integral. So if you want to compute divergence, not a distance, but some kind of measure of dissimilarity or similarity, right? Well, it's actually dissimilarity because when KL-divergence is 0, well, plug P instead of Q, you get log of 1, and KL-divergence is 0. So the nice property of KL-divergence is non-negative, and the minimum is at 0. But the bad property of KL-divergence is it's not symmetric. Well, but if you look at just this part, so it's an integral with this probability of x over all possible values of x, which is nothing but an expectation, as I said, of x with respect to probability p, expectation of this log of this ratio under probability p. KL-divergence. But if we rewrite that, well, log of ratio is nothing but log p minus log q, and then linearity of expectation, well, integral of a difference is a difference of two integrals. Nice. Then we have two quantities here. And from this, we see that KL-divergence could be interpreting as measure of an extra number of bits needed to send a message containing symbols drawn from probability distribution P when we use a code that was designed to minimize the length of the message drawn from probability distribution Q. In other words, we have cross entropy of P and Q minus entropy of P. So this is minus entropy of P, and this is cross entropy of P and Q, as you can see from verify from definitions of cross entropies. So because this code is suboptimal when P is not Q or when Q is not P, then we know this is larger than the entropy. The cross entropy is larger than the entropy. So now you know what KL-divergence is, and you see that if we switch P and Q places, it's not going to be symmetric. So if we swap this, the result will be different. So it's worth thinking a little bit about what will the difference be. And this one is from the deep learning book by Goodfellow, Benjo, and Corville, chapter 5. A nice illustration. So the point is, when we are computing the normal notion of KL-divergence, or the most frequent, I should say, what we're trying to minimize or maximize, we're trying to fit, and then say we chose a totally wrong functional form for Q. When we minimize KL-divergence, again, as before, we are thinking that our Q is parameterized by some theta, some parameters. And to minimize KL-divergence, the distance between those distributions, we are optimizing with respect to theta. We're changing those parameters such that to change Q for KL-divergence to be minimal. To find such a Q in the family of all Qs that minimizes the KL-divergence. In this case, Q will try to occupy as much place as possible, so as much place where P is positive as possible. So it will sort of stretch in the bimodal case. But if we swap P and Q, then the optimal value, or the value where KL-divergence will push the Q star or the Q that we optimize for, it'll push it to one of the modes in order to not make any mistakes. Like this swapped or mirrored KL-divergence penalizes the places where P is 0 or very low while Q is high. Heavily penalizes those places. So when you optimize in quote unquote incorrect, well, yeah, when you optimize, let's leave it at that, quote unquote incorrect KL-divergence, you're not capturing the full P distribution, but you're making sure that your Q is not producing false positives. Like P generates high probability for something, Q generates high probability for something that is actually low probability. And correct or incorrect is relative in the technical world because everything should be thought about, considered, and used in accordance with your problem. If your problem calls for the use of correct KL-divergence, please go ahead and use the, okay, quote unquote, or more conventional KL-divergence notion. But in some problems, this is fine. And it's again, think about false positives or false negatives depending to the tasks that you're solving, relative to the task that you are solving. Now, why did I tell you all of that about what was it about and how it is related to the main point of our lecture, maximum likelihood estimation? Well, maximum likelihood estimation, in fact, is KL-divergence minimization. I'm going to see it now really quickly. Remember, our estimate, MLE estimate of theta, which is this, another way to draw it. So this and that, those notions, I could just write the same with Q, parameterized by theta. That's what those two writings basically refer to. This is our MLE, maximum likelihood estimation. We want to find such theta which maximizing the likelihood, which maximizes the likelihood. Because we are assuming our data set D is drawn IID, independent identically distributed, we're saying that it's equivalent to the product of individual, our likelihood is equivalent to the product of individual samples. And imagine when n is large, all of those values are less than 1, and the product of many numbers less than 1 is hard to handle because of the underflow errors and things like that. Again, please check this paper and what every computer scientist should know about floating point numbers. But in any case, numerically, really undesirable notion. And so to correct for that, we usually instead take a log. And when we take a log is monotonically increasing function. What will change is the actual value of the function. So say, for example, if our function was like that, and then there was a maximum here, and of course, I'm totally an illustration, that's not how it will look, but imagine that if we took a log, it'll be wrong, exactly the point I'm trying to demonstrate. So if we took a log, the maximum will be different. The maximum value will change. It was here, it will move there, but the location of the maximum of this function and that function won't change. They will be the same. So theta MLE that maximizes this expression will be the same. So, okay, we introduced log. Well, I hope it now starting to look familiar. Notice that the axis, the data, is drawn according to probability distribution P, while we're measuring the probability or likelihood with Q. Make sense? Yes. This is pretty much similar or the same as this. We are taking an expectation of log of Q with respect to P. What is that? Negative cross entropy, right? So when we maximize this quantity, we are minimizing KL-divergence between the data distribution and the distribution that we're trying to feed to the data. Imagine that the data was generated from the same family of distributions, like the data was generated from P, Q, theta star, and we're starting with P random theta. So what we're trying to do is we're trying to minimize KL-divergence between those two distributions, which pushes our estimate of theta towards theta star, eventually to 0, because that's possible in this case. But that's a neat connection and explanation. Maximizing likelihood or MLE estimate is actually minimizing KL-divergence.